It's January 25th at 11:31 p.m. exact time. I'm looking at my notebook and my knots. I've been trying to put my knots into order. Here's one knot that I found. Here's the extended Gauss notation. Here is the loop here going minus and positive. That's this loop right here going under and over. Now if this loop were to move around right here and then move around right here, we would have this knot. You can see the loop was previously here, it's gone to this position, then to this position. Here's the extended Gauss notation. You can see the loop right here. It goes positive, then negative. Here it comes positive, then negative. And it's gone two spaces, because if we go back two spaces, if it goes 1, 2, it should be before the 5, after the 2. And you can see right here, before the 5, after the 2. Now this knot here in the middle, I've drawn it in because I actually haven't found that knot in its physical form, such as this, bearing in mind that this is a 3-flip Mobius strip that's been cut down the middle with this cross number of 6. It's been represented here in knot notation and a knot diagram, and I went and made this knot, but I speculated. I took this loop right here and I moved it one place to the 2, then I drew the knot notation. You can see the loop was here, but now it's here, and I didn't know it was a positive or negative, and I thought, well, if this loop going over then under keeps the same orientation, if it goes under this side here with rearranging the paper form, then it should be over than under, and I think that it should be on the inside, such as here. It stands to tell that it's on the inside here. When it comes in here, it'll be on the inside here. So I went and made that knot, and this is it. And surprisingly, here's the 6th loop right here, but you can see previously it was right here on the inside, and I thought it'd be on the inside here, but it's on the outside. Here's the knot diagram. You can see the loop right here, and I thought it would have been on this side, but it's not, and I don't understand why it's in that orientation. So it's very confusing. Like, it's so hard to tell what form these knots are going to take. You can predict the knot notation, but you can't predict what form the paper is going to take. Now there might be a knot paper form that will have this loop on the inside of the boundary right here, but I'm not sure. And it's funny how the paper forms obviously don't match perfectly the knot notation, and so far it's proving slow to count all the knots and understand how the knots work and to speculate on how many knots there could be. So one thing's interesting, they all have a wanting number between 2 and 5. For example, this is the beautiful one. It's the coil that I've done. Here it is right here. That has a wanting number of 5. It's the highest wanting number for a knot. All the rest sometimes have a wanting number between 2 and 3. So I push on. We got some knot families. Here's all the loops, knots with 2 loops. Here's more of the knots with 2 loops. Here they are with 3 loops, with 2 loops. And here's all the knot notation. Here's some of the knots I've been ordering. And I've been working on, that's it, flattened down the page. I've been looking at the graph. They all have 10 edges, 10 vertices. Here's a standard Mobius strip with 3 flips. It's just been flattened and drawn. It takes 1, 2, 3, 4, 5 creases to flatten it. But when you cut it down the middle, it takes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 creases to flatten it. And if you can find that paper form, it might be here somewhere. Oh, here it is. Here it is. Here's the Mobius strip that's been cut down the middle. It has 8 twists in it, and it's been flattened with 10 creases. That's it.